Okay, so we're going to start out our lesson on alkynes. So alkynes, as you guys know, just a functional group that is a triple bond. And one thing about alkynes that I think can be a little confusing when you're just getting started is that there are carbon atoms on either side of that triple bond. So if we look at this point and this point, those are carbon atoms. And I point this out because, when you're drawing something like this, where you have an alkane, there's this directional change here. I'm going up, I'm going down. And it's easy to see that that's a carbon and that's a carbon, but it's very easy to lose these carbons if they're not explicitly drawn. So I'm not going to explicitly draw them out all the time, but you may want to do that until you get a better handle on how to work with these things. It takes a little while for the brain to kind of pick up on what's going on there. Yeah, nomenclature we can go through very fast. So if we look at nomenclature, we could just pick out some really simple molecule here. Here we have the end fix, or whatever you want to call it, ANE. Now it's going to become YNE. And we're going to number such that we give the alkyne the lowest number along that carbon chain. So here we have hexane as the parent, because we've got 6 carbons, but since it's an alkyne, we're going to call it hexyne. Actually, let me just switch to print here. Hexyne. And then, of course, we want to say where the alkyne is, so we say 2. And that tells us that the triple bond is between 2 and 3 right here. So we always put the lowest number and assume that the triple bond, or in the case of alkenes, the double bond, extends from the lowest number to the next highest number. So 2 implies that the bond goes from 2 to 3, not 2 to 1, for example. Okay. Let's get to some chemistry now. So eventually we're going to get to maybe one of the more important reactions that you learn in the first course that allows us to form carbon-carbon bonds, which is kind of the whole point of the entire field of organic chemistry. Before we get to that, let's just start out with some other reactions. So the reactions that you learn for alkynes are very similar conditions, at least, to alkenes. So remember, for alkenes, we could use hydrogen and some sort of precious metal to do a reduction. And the same thing is true here. So if I take hydrogen and I add in some platinum, I'm going to do a reduction, so I'm going to add hydrogen across that pi bond. We'll get somewhere along the way, right? We're not going to add 2 hydrogen molecules simultaneously. Somewhere along the way, we're going to form that alkene, but we can't isolate that. And it just keeps going until it goes all the way to the alkane. Okay, so if I take a precious metal and some hydrogen gas and I bubble it through an alkyne, I can get rid of the triple bond altogether. So, if we wanted to stack this somewhere in our flashcards, you might say something like alkyne to alkane. Okay. But there obviously might be examples or times when you don't want to go from the alkyne all the way to the alkane. And so chemists have discovered other conditions that allow us to stop before we get all the way to the alkane. So if we take H2 and we use something called Lindlar catalyst, Lindlar catalyst is a precious metal, but it's been poisoned to make it less reactive. So it's not as good as a catalyst as like just straight up palladium would be, or straight up platinum or something like that. And the result of that is that we can actually stop this at the alkene. You'll notice, just like with the addition of hydrogen gas to an alkene, it goes syn. This is also going to be syn. So we end up with the cis alkene, there's syn addition here, if we're talking about the stereochemistry. So here, we're going from alkyne to alkene. And then you might want to indicate, if you're making flashcards or trying to remember this, that this addition goes syn, or it forms the cis alkene, something along those lines. Okay. So still, if you can do, so maybe sometimes you want to have the trans alkene. So, we have a way to reduce an alkyne down to an alkane. We have a way to make a syn or a cis alkene. But we might want to take an alkyne and actually make a trans alkene. How do we do that? For this one, we're going to use sodium. So this is sodium metal, not like sodium cation, like table salt. This is like metal sodium. Stuff's really reactive. It's kind of not a super uncommon demo to see people put it in water, and it'll just kind of catch on fire. I like to put a little 0 up there just so I'm not tempted to think of it as sodium plus. But yeah, what this allows us to do is to make the trans alkene. So again, we have alkyne, and we're going to alkene. The addition here is going to be, anti. You're going to form the trans alkene there. So 3 different reductions. This first one at the top, if we look at this one, we can get an alkane. Here we get an alkene, but we get the cis alkene, and then here we get the trans alkene. And this is going to be kind of common where you're starting with a starting material, you want to get different types of selectivity, stereo or regio, and then chemists have developed all these different reagents and conditions to do that. Okay. So, what about some other reactions? We can also do an addition reaction. So that was a really common theme in the alkene section. We did a ton of different addition reactions. If we add HBr to this, what we end up getting out is this. So you'll note that the bromine is adding to the last substituted carbon here. Okay, so it has 2 shots, or 2 different places it could go. It could go to either of these ones, carbons that are highlighted in green, and it goes to the more substituted of those 2 carbon atoms. So we would say this is Markovnikov. And then we would also, let's see how this in our notes, we might say something like, excuse me, alkyne to I would call this like a vinyl halide. You might call it something like an alkene with a Br. It's kind of whatever is useful for you. Vinyl implies that you have a bond directly attached to the carbon atom that has a double bond to it. So this position for this hydrogen atom that I've just drawn, that's the vinyl position. So if I put something, if I put something else on there, if I want to put something like a chlorine or something, now I've got a chlorine in the vinyl position, or a bromine like in the top. All right, so that just means that it's attached directly to the double bond. Okay, but we know that if I use HBr and alkenes react with HBr and I'm forming an alkene, you can imagine that if I take and I use a big excess of this, that it'll just keep reacting, right? So instead of stopping at the alkene, like we did up here at the top, that alkene can then just keep going to go and react more if you have an excess of HBr in there. So up here we're working at sort of this stoichiometric, conditions, meaning that we have 1 mole of HBr for every mole of alkyne that we have in there. Down here, we have more than 1 mole. We have 5 moles or something. Doesn't really matter. We have too much. So what ends up happening is, at first we form this, but then because we have excess HBr in there, we end up forming at the end is this. So if we look, we just add another equivalent of bromine here. So again, it's kind of like Markovnikov addition. It just adds to that same carbon twice. So by changing just the concentration of HBr, we can get 2 subtly different products, or 2 different products, but it's a subtle change in reaction conditions is what I should have said. So this would be going from an alkyne to, we would call a geminal dihalide. So geminal is a term that just means that they're attached to the same carbon atom. So in this situation, I've got a bromine and a bromine, and they're both attached to that carbon atom that's highlighted in green. We would call that geminal dibromide or something like that. Okay, what if we want to add a bromine to the less substituted carbon here? So we have these 2 carbons here. This is the more substituted one. I'll highlight this one in kind of pink. That's the less substituted one. In the top situation, up here, we're not adding it to that one. We're adding it to this one. So now we're going to try and add it to the pink one. To do that, again, just a subtle change in conditions allows that. We take HBr and we add in hydrogen peroxide, which in the middle of a pandemic is going to be very difficult to find. So hopefully you don't have to do this reaction in real life. And what we end up getting out of that is bromine at the less substituted carbon atom. So this might be considered like anti-Markovnikov. And you'll notice that for this one, I have drawn out both stereoisomers. You might see one over the other, but you're probably going to see both. Anti-Markovnikov. And so here we have an alkyne going to a vinyl halide, but you have to note somewhere that this one goes anti-Markovnikov. So yeah, when you come up here, you want to say, probably make sure that you have in your notes, Markovnikov. Wish it was a guy with a name that was shorter who had it attached to this selectivity idea, but what can you do? All right, so again, changing our conditions, showing that we can get different selectivities and such. Ultimately, we're pushing towards being able to string a bunch of reactions together to do some organic synthesis. So we're going to have a goal here, and that'll make more sense, I think, by the time we get through this section on alkynes in its entirety. But okay, let's look at another reaction now. So let's say that I have an alkyne. It's an internal alkyne, meaning that there's no hydrogen on either side. If this was a hydrogen, or this was a hydrogen, we would call that a terminal alkyne. That's what we're dealing with up here. Here we're going to say it's internal, meaning that it's not at the terminus of the molecule. It's somewhere in the middle. If we were numbering this and naming it, the alkyne wouldn't be on 1. Okay, so I've got this internal alkyne, and now I'm going to do something similar to what we did with alkenes. We're going to do acid-catalyzed hydration. Because it's an alkyne, they're slightly less reactive. We're going to have to add mercury sulfate in there. Mercury sulfate acts as a catalyst to kind of get things going here, make that alkyne more reactive. What we get out of this is the addition of an alcohol, and it goes Markovnikov. The tricky thing here, or the twist, I guess I'd say, is that it doesn't stay an alcohol. It becomes a ketone. And we call this, we use this fancy word for this, we call this a tautomerization. And the reason, or what a tautomerization is when you take a proton and you move that proton, and you get a new constitutional isomer out. Right? So we've broken a bond, we've formed a new bond, but it's just between a proton. That's what a tautomerization is. And this is really the only tautomerization that we worry about, at least in the first course. But so if you take an alkyne and I treat it with this sulfuric acid mixture, it'll go to an enol, meaning that it's an alkene, because it has a double bond, and also an alcohol, because it has a hydroxyl group on it or whatever. But it doesn't stay an enol, so it really goes to a ketone. So you could put enol maybe in brackets, and then put ketone at the end. It's unusual for it to form an enol and it to stay an enol. There's obviously exceptions to that, but generally you're going to go from an alkyne to a ketone. The enol that you form is going to go Markov. I'm just going to start shortening this guy's name. It's going to go Markovnikov. If, let's see, did I lose a carbon atom? I sure did. Go add that back in up here. So I've got 1, 2, 3, 4. 1, 2, 3, 4. Okay. There we go. That fixes that. Okay. All right. Yeah, so that's Markovnikov. So just like when we looked at alkenes, we could change our conditions for making an alcohol and get anti-Markovnikov. We can do the same thing here. We're not going to use an identical reagent. Remember, for that we use BH3. Here we're going to use something called 9-BBN. And what we're going to get out of this is an alcohol, but the alcohol is going to be at the less substituted carbon. So again, we have this choice where we can be at the more substituted carbon atom, the less substituted carbon atom. If we use acid-catalyzed hydration, we would get a substitution at the green carbon atom. Here we're going to use this other reaction, this hydroboration-oxidation, and we're going to get substitution at the less, or sorry, we're going to get a reaction at the less substituted carbon atom. And again, you'll notice that we formed an enol here. And we know those aren't stable from our last example. That's going to immediately tautomerize into an aldehyde. So here we have a method of going from an alkyne to an aldehyde. So if you're wondering why we're using, actually let's say here we're going from an alkene, this is kind of how I might remember it, to an enol. That's anti-Markovnikov, and that ultimately rearranges to an aldehyde. If you're wondering what 9-BBN is, yeah, it's normally we'd use BH3 for an alkene. 9-BBN is actually this kind of big bicyclic looking thing. And the reason we use that has to do with the mechanism for this. Since you're forming, if we use BH3, since you're forming an alkene, the BH3 could react with the alkene as it forms. And that causes some problems. I didn't make you learn the mechanism for that, so that's probably a little bit difficult to see. But 9-BBN prevents that from happening. 9-BBN is not the only type of reagent that can do this. Any kind of bulky boron reagent with a hydrogen on it like this can do this. But 9-BBN is kind of the common one. That's the one we'll use. Okay. Yeah, we can look at some other reactions. Similar conditions again to what we saw for alkenes. If I take some generic alkyne and I subject it to Br2, I get the I get a trans bromide out of it. So 2 bromines on either side of the double bond. If I use an excess of that, then it'll, the reaction will keep going because alkenes are really reactive with bromine. Then I'll end up getting this tetrabromo compound. Put excess next to this. So again, just changing the reaction conditions a little bit gives us a different product. So in this case, we're going from an alkyne to like a trans dibromide. And in this case, we're going from an alkyne to tetrabromide. We'll say this is an alkene as well. Okay, and then finally our other, just generic type of reaction that we're going to learn for alkynes is ozonolysis. So I'm going to use the same conditions we used for alkenes, only now, so remember when we looked at alkenes, we would take this, the double bond, and we'd cut it in half and then cap it with oxygens. Here, instead of doing that, we're actually going to form carboxylic acids. So it's the same kind of thing where you just break the bond altogether, but instead of the bond that breaks, let's see, instead of this bond that breaks here, forming two ketones, now instead it's going to form two carboxylic acids. If I have instead, let's say, not a terminal alkyne, but I have a hydrogen, I'm sorry, if we have instead a terminal alkyne and not an internal one, again, we'll get a carboxylic acid, but what are we going to get on this other side? When we do the split, yeah, we're going to get just carbon dioxide gas out of it. So, there's basically no time that you'd ever want to make carbon dioxide in an organic synthesis scheme. That's going to just be a side product for that reaction, but it's just the other thing that you get. Okay, so in this reaction, if we want to make a note, we've got an alkyne, and now we know how to transform that into a carboxylic acid. Okay, so we've got a lot of reactions that we learned in a pretty short period of time. You want to make flashcards, combine this with the alkene stuff that you know, and start sort of cataloging these things in your brain. And we're going to learn a new reaction in the next video for making carbon-carbon bond, and that's when things start to get a little bit interesting and allow us to build some sort of neater looking structures. So right now we're looking at, I'm starting with an alkyne, I'm making carboxylic acid, I'm sort of transforming one functional group to another. We're going to learn this carbon-carbon bond forming reaction. That's going to be kind of the start of our real education in how to do these reactions.